The current practice of using mechanics of a damaged medium equations for different mechanisms of resource exhaustion suggests that this approach is efficient enough for practical applications. It is sufficient to evaluate correctly the process of resource exhaustion of structural elements and components of load-bearing structures. In the present work, we developed a mathematical model of the mechanics of a damaged medium used to assess the durability of materials and structures in fatigue and creep. Laws of damage accumulation in structural alloys affected by fatigue and creep are analyzed using numerical modeling and by comparing the obtained results with the experimental data. Model of a damaged medium consists of three interconnected parts. Defining relations describing viscoplastic behavior of material, accounting for its dependence on the failure process. Evolutionary equations describing the kinetics of damage accumulation. A strength criterion of the damaged material. In an elastic region, the relation between spherical and deviatory components of stress and strain tensors are established using the Hooke's law. Effects of monotonous and cyclic deformation in the stress space are accounted for using a Mises form of the yield surface. To describe complex cyclic deformation modes in the stress space, a cyclic memory surface is introduced. For the yield surface radius, the following evolutionary equation is assumed. To characterize the behavior of the memory surface, the following evolutionary equation is introduced. Proportionality coefficient for each of the three sections of the creep curve is defined as shown. The structure of the evolution equation of the fatigue damage accumulation will be presented in the following form. The evolution equation for the creep and summation of fatigue and creep damage are expressed as shown. The condition when the damage degree reaches its critical value is taken as a criterion of macrocrack nucleation. This slide shows the numerical analysis of the problem of evaluating fatigue life of steel 304 under block-type cyclic loading with the increasing and decreasing cycle amplitudes. Linear damage summation hypothesis results in this case in both underestimating with a margin and overestimating the value. The case of increasing strain values, the damage summations exceed unity. The law of linear summation of damage yields a conservative error. In the tests with decreasing strain values, those sums are less than unity. The law of linear summation of damage leads to a non-conservative error. This slide presents the numerical analysis of the problem of evaluating thermal cycle fatigue life of the mnemonic 80A heat-resistant alloy under isothermal cyclic loading, in-phase and counter-phase variation of mechanical strain and temperature. The computational and experimental results show that low cycle fatigue curves for various deformation trajectories are computationally reconstructed to a high accuracy. The model of the damaged medium accurately enough describes the processes of isothermal and non-isothermal deformation and damage stress accumulation for combined thermal mechanical loading. For non-isothermal deformation model in this temperature range, the mnemonic 80A heat-resistant alloy is insensitive to phase dependence of changes in temperature and mechanical deformation. This and the next two slides show the numerical analysis of thermal cyclic fatigue life of a compact specimen with the concentrators in the conditions of a complex multiaxial stress-strain state. This slide shows the history of change of components of strain tensor and temperature in the concentrator zone. It is shown that the linear damage summation hypothesis results in both underestimating and overestimating the value. Next, we present the numerical solution of the problem of evaluating thermal cyclic fatigue life of combustion chamber flame tubes with various inclinations of the coolant channels. The model of the jet engine flame tubes with inclinations of coolant channels and history of thermocyclic loading are shown on this slide. This slide presents temperature fields and stress fields for a tube. On this slide, damage degree is shown as a function of number of thermal loading cycles for different inclinations of the channel. This slide presents experimental setup for analyzing short-term creep of steel 304. The depicted creep curves are for the angle theta of 30 and 90 degrees. These creep curves are for the angle theta of 150 and 180 degrees. Analyzing the obtained numerical results in comparison with experimental data shows qualitative and quantitative agreement. Certain discrepancies between the computational and experimental data can be explained by the following: inaccuracy in assigning material parameters and scalar functions. The experimental information is represented without accounting for the scatter of experimental data within each individual test. The experimental results testify to the presence of plastic strain, which was not accounted for in the computations. When processing experimental data, the incompressibility condition of the material was taken into account. Thank you for your attention.